Can you hear me okay? Okay, cool. Good thumbs up. Not checking my text. I got an extra timer there for redundancy. Okay, raise your hand if you've ever edited an NGINX config file. Okay, raise your other hand if you forgot the semicolon. Okay, and then put your head in your hands. And then you just shake it like this. And this talk is about me doing that like 500 times a day for like several months. I want to start by introducing you to me, the repeated head holder. My name is Sam. I contribute to OpenTelemetry Ruby. I'm on GitHub at PlantFanSam. I really like to shoot the breeze. So if you want to come and talk to me about anything, please do. I work at Shopify and I do tracing stuff there. If you don't know, Shopify is the world's commerce platform. We scale you from hello world to IPO. I have a family member that makes her full-time living on her Shopify store, and I'm really proud to work there. So in addition to liking Shopify, I also like diagrams. Here is a diagram of the before state that the talk will address. So on the bottom, we have the different blocks that comprise like everything that happens during a web request. You got the CDN, then the proxies, then application code, service-to-service calls, etc. Prior to this work, logging had this more extended view of the request than tracing, and as we learned from day one of the conference, traces are the best signal. So what we're going to talk about is this red. I guess it doesn't look that. Does it look red? This talk box, medium red? Anyway, we're going to talk about that little box. Incidentally, this is that red box. That off-white box is what specialization looks like in post-industrial capitalism. That's my job right there. The red box has three parts to it. I want to start by showing the end state, by showing like what does tracing a proxy really look like. And then I will discuss the strategy that we took, the choices we made, and then I want to talk about how we productionize this and do a little bit of demo, try to do a little demo. Could get a little hairy with the multiple screens here, but we'll see how that goes. So without further ado, I would venture to guess that most Monitorama attendees have seen a trace before, but here's one that I helped make. You can see there's three spans. It's a little pixelated, it's okay. There's three spans. The first one is a global proxy, the second is a local proxy, and the third one is an application span. And you may be thinking, okay, well, big whoop, why do I care? The reason that we care is sometimes the traces might look like this. You can see the first span starts at 0, whatever, and then there's, maybe 100 milliseconds of network latency, and we want to figure out, hey, like, why is that actually happening? What's going on here? What's going on here is that the first server is in, I believe, Mumbai, and the second one is in Council Bluffs, Iowa. So it's going across the planet, and then it's transiting the planet again, going under the ocean, and that's why it is slow. So we made some strategic choices in order to get to this point where we had this kind of visibility so we could do sort of spot checking and quantitative analysis. We had two main questions to address. The first one was, did we want to use OpenTelemetry or something else? This isn't just like a straw man for a group of people that clearly likes OpenTelemetry a lot. We had a previous proof of concept that was getting us traces out of NGINX by using a Zipkin package, and you can just kind of rig up your collector to have the Zipkin receiver, and you can go on your merry way. So that was working-ish, I would say like 55% working. But on the other hand, Shopify loves OpenTelemetry. I also love OpenTelemetry. We use OpenTelemetry to say the same thing for the fourth or fifth time in a row. We use it for tracing, and we have a lot of folks that contribute to OpenTelemetry Ruby and OpenTelemetry Ruby instrumentation on the staff at Shopify. Also, hi to all the OTel Ruby maintainers. If you're watching, Ariel, Rob, Matt, Eric, if you're there, hi. The other important thing about Shopify loving OpenTelemetry is that we're sort of fluent in the OpenTelemetry domain model, which I agree with earlier speaker who said that the domain model is a really important part of the whole pitch. And we knew that we do have a custom trace propagation format, so we were going to have to kind of crack this thing open and muck about anyway. So we thought, hey, why not do OpenTelemetry? So knowing that we wanted to do OTel, the other major question was, do we want to use OpenTelemetry C++, or do we want to use OpenResty directives? If you are not familiar with OpenResty, I think it's the next slide, so bear with me. OpenTelemetry C++ has a contrib repo that has an NGINX module that will let you trace NGINX. However, it did not play super nicely with the way that we compile NGINX at Shopify, and that was a discovery that was made by someone that left the company, so I thought, well, better just not touch that. I don't want to fight with a build problem in a language that I don't know. So I thought, well, we have OpenResty kind of working with Zipkin. Let's try to use OpenTelemetry, and we'll have a lovely working system. The other thing is that Shopify currently does a lot in OpenResty. The proxies are doing some really, really interesting stuff. So having Lua instrumentation, the ability to instrument Lua in general in a format that we know and love, OpenTelemetry, would be really valuable. And moreover, there was already a library for OpenTelemetry Lua, not officially part of the OpenTelemetry GitHub org, but it exists. And there was an implementation of tracing in API 6, which kind of looks a little bit like OpenResty. So what is OpenResty? Well, this is an NGINX config file. And you can see here that OpenResty will allow you to embed arbitrary Lua anywhere you want. You can do math, you can set variables, whatever you want to do. And each of these blocks is known as a directive, unless I'm butchering the terminology, which is totally possible. But basically, the init worker block will run when the NGINX worker boots. The rewrite worker block will run when OpenResty receives the request, but before it sends it off to the upstream that's going to actually generate the HTTP response. And then the log by Lua block will run sometime in the future after the response has been returned to the user. So this is, kind of where you're going to need to shove your Lua if you want to trace NGINX using Lua. And we use Ingress NGINX as a way of deploying OpenResty. If you're not familiar with Ingress NGINX, basically the premise is that you have a config map in Kubernetes, and when you change stuff in the config map, it updates the NGINX config file in your NGINX containers and sends, I forget what signal you send the NGINX process to restart it, but it does that for you, keeps them all in sync. It's really nice. And fortunately, Ingress NGINX also has a plugin system for OpenResty. This is kind of the shell of a plugin in Ingress NGINX. You need to have a Lua table that is encapsulated as a module, and you basically get to fill in the guts of all these methods with whatever you want to do. And then during that init worker phase, it'll call the init worker method. During the rewrite phase, it'll call the rewrite method, and so on. So that led us to this fairly naive implementation of tracing in OpenResty. I'm just going to talk through the code here. So on the first line, what we're basically doing is instantiating a Shopify custom propagator because we have our own tracing format as previously discussed. And then in the second line, we're instantiating a new OpenTelemetry context object, which is a little bit of inside baseball for the OpenTelemetry SDK, but effectively that's just where you shove the trace ID and the span ID, among other things. And then we're going to pretend like the m.tracer method is implemented, but you just grab a tracer, which is what generates spans. And then on the next line, we're reading in the inbound nginx.rec. So that's got the HTTP headers on it, so you can extract the trace ID and span ID, and that will return an inbound context, which will either point to the trace ID that was present on the inbound request, or it'll create a new trace ID, and it won't have a parent span ID, so it'll be the root of the trace. And then the next line, we start a span, and we pass in that inbound context, and we're going to call nginx.request. And then on the subsequent line, if you're still with me, it's 2 above the end in the rewrite method. We inject the new trace ID and or span ID into the HTTP headers that we then forward on to the application that's going to generate the response. And then there's this special variable in OpenResty, NGINX.ctx, which is local to each web request. So if there's an NGINX worker that has, it's dealing with 10 concurrent web requests, each of those will have its own isolated table available at ngix.ctx. So we store the span on there. And then during the header filter phase, which is basically after the, I guess the application's over here and the client is over here, and I'm OpenResty. So when the application server returns a response to OpenResty, OpenResty has a chance to do various things before it returns it to the client. And what we do in that phase here is we finish the span. And that's pretty much how you naively get some spans out of NGINX when you're using OpenResty. That took a really long time to get working, but it ultimately did. We had it running in staging. And I want to talk a little bit about productionizing. So this is, there's a reason I took a drink there, because for context on productionizing stuff at Shopify, this is the horrifying reality of my life. Shopify served almost 76 million requests per minute on Black Friday, Cyber Monday peak in 2022. There's like a link to a tweet at the bottom where the engineering department, said that. And I'm sort of just trying to make changes to this extremely performant system, which is just a little bit scary. And when I'm worried about scary things in production, instead of generally worrying, I try to start worrying about specific things and make a list of stuff that I'm worried about. So this is basically what I was worried about. The first was, how are we going to get the spans out of OpenResty in a performant way? And doing so will allow us to not DDoS ourselves. If we were going to basically send a request to the collector on every request, that would be basically DDoSing ourselves. So fortunately, OpenTelemetry SDKs use a construct known as a batch span processor, so we wanted to use that. If you're not familiar, when you finish a span, there's this little, that span goes into a batch span processor, which has a buffer somewhere in memory, and there's slots for spans to go into. And as it fills up, it will eventually reach a threshold, at which point it will export the spans. You can export spans however you want, but a network call is usually conventional. And then the buffer empties out. So we knew that we needed to use this construct of a batch span processor. However, if you think back to the example of what does OpenResty look like in an NGINX config file, it's kind of just a pile of Lua. So how are we going to make sure that this all works properly? In order to do that, you have to start freaking out about the process model of NGINX and OpenResty. There's like a ticket representing this work that I did, I guess, 7 or 8 months ago. And it's just like me trying to figure out are we going to run into all kinds of problems with different threads writing to different stuff? So eventually I figured out what the NGINX and OpenResty process models were. There's a really great blog post on the NGINX website that goes into a light explanation of how the NGINX program models its different worker processes. But basically there's a master process that does all kinds of privileged stuff like binding to ports, etc. And then it spawns child processes. You can just ignore the ones on the left, which are related to caching, but it generates, it has these child worker processes which handle HTTP. They have HTTP state machines that manage different requests. And each of these workers, says the blog post, runs, wow, can't read that. They run single threaded, and there's a link at the bottom. So that's NGINX. OpenResty is an NGINX module that interacts with the NGINX event loop in ways that I do not understand. So for that reason, OpenResty, I sort of saw the OpenResty README in quasi-religious terms. I could quote chapter and verse what the OpenResty README said about different promises about the runtime. So I'll commit the cardinal sin of reading text on a slide during a presentation. To globally share data among all the requests handled by the same NGINX worker process, you're going to encapsulate the shared data into a Lua module, use the Lua require built-in to import the module, and then manipulate the shared data in Lua. Those NGINX worker processes, those are those square W's. I think of them as square W's now. So some more reading from a slide. It is usually recommended to share read-only data this way. You can also share changeable data among all the concurrent requests of each worker process as long as there is no non-blocking I/O operations in the middle of your calculations. Fingers crossed. For this reason, always be careful when you want to share changeable data on the worker level. So this had me shaking in my boots. We have a lot of traffic, an ideal situation for race conditions. But that led us, so we had this like, overall, the situation is, NGINX has a master process with n child worker processes. They scale with CPU cores generally. The child worker processes all run single-threaded because the blog post said so. Each request in an NGINX worker process shares the same Lua interpreter. That was not on a slide before, but it is true according to the holy text. And you can share changeable data across concurrent requests that are fielded by the same NGINX worker, as long as you don't mess it up. So that left us with the following strategy. So on booting each NGINX worker, we instantiate a batch spam processor and store it on a Lua module instance. All of the requests fielded by a given worker will push to the same batch spam processor, and that batch spam processor will manage its own export pipeline, and we're going to try not to mess it up. So on the topic of not messing up, I'm going to try to do a demo real quick. We'll see if I can manage this screen situation. Okay. All right, so a little bit of lag using the cursor here, so forgive me. So what we have here is basically a code space in GitHub. I think code spaces are cool. So we have an OpenResty config, and what I'd like to show is that there are two worker processes, each maintaining their own export pipelines. So we configure this to have two worker processes, and when we initialize the worker, we're going to run BSP, we're going to require the Lua module, and we're going to run the init worker method, and then when someone hits the demo, endpoint, we're going to run the BSP demo rewrite method, and then the BSP demo log method. And the contents of that file, really exciting sentence to say. During the init worker phase, we instantiate a batch spam processor, and we're going to set the max queue size equal to the process ID of the NGINX worker. And then we create a tracer provider, which the batch spam processor is the only positional argument that you provide to that. And then we're just going to log out the worker PID and the max queue size. And then during the rewrite phase, we start a span. We're not going to deal with context propagation. We're going to log out the worker process ID and also the span ID. And then we're going to tack that return span context onto the ngx.ctx table. And then during the log phase, we're going to wrap things up and finish. So I wrote myself some instructions. So we'll see if they work. If they don't work, at least it's not production, right? Let's see. How am I doing? Oh, I'm missing an R. Let's see. Do I have Vim mode enabled here? No. Okay. We're just going to have to wait for this cursor. So how's it going? Okay. Big bucks, no whammies. Okay, look at all that green. So we're going to start another window. I'm going to hunch over. And we're going to just curl this 6 times. And maybe it's in the shell history. Let's see. Nope. All right. I'm sure people that are better at text editors than me are infuriated by the way that I am selecting text, but I assure you it is because I am looking at a screen with a significant delay. Okay, so what do we got? 4i, okay, that should do it. Nope, backtick. All right, one more. Okay, so in our demo logs thing, you can see when we boot the worker with PID 8, or with PID 7, the max queue size is 7, and when we boot the worker with PID 8, the max queue size is 8. So we have 2 of these going. And what I want to show, one of the unfortunate aspects of this project is that viewing NGINX logs, error logs are not, you can't really customize them very easily, so this was kind of my reality. And you know what, we're not seeing any stuff fielded by worker 8, so I'm just gonna curl a little bit more. Okay, so here you see worker ID with PID 7 is fielding the span ID 5F99. And down here you can see worker with PID 7 has that span in its export. And worker with process ID 8 has the span ID 2359. And you can see that is in the list of spans that it exported. And that is my extremely exciting demo. I'll go back to my presentation now. I feel great that it didn't go, well, that it sort of worked. Let's see. Maybe we should look up a word to describe how I'm feeling. All right, so back to the slides. Should be at 18 minutes here. What do we say? Well, I'll just keep going. You can take the hook out whenever you want. All right. So, resiliency and performance, demo complete. Don't break the site, as they used to say at a company I worked at. So, if the span buffer is full, those 8 square boxes, and we are we're finishing more spans, and there's nowhere for them to go, we have to make sure to throw them away to prevent unbounded memory growth in our OpenResty instances. So that was just a matter of verifying that the library behaved that way, which it does. Very cool. It's actually an option that you can toggle, and I don't know why you would turn it off. One interesting part of OpenResty that will blow your mind is that you can do background jobs in NGINX by using the timer at API. And so the batch span processor in OpenTelemetry Lua is using timer at when it queues that. So if you finish a span in the middle of the header filter phase, you don't go ahead and try to make an HTTP call to the collector before you return the response to the user. We added a circuit breaker and backoffs for calls to the collector from the OpenTelemetry Lua SDK. What we saw was that if the collector was having some issues, then OpenTelemetry Lua would just try to repeatedly protobuf encode the payload and just again and again basically DDoS ourselves and also spike CPU in OpenResty, which is bad because if you recall, workers are CPU bound. We ended up speeding up trace and span ID generation by 92x by tweaking the way that we generated random numbers in OpenTelemetry Lua, which is the single greatest improvement that I have ever made to performance. On a multiplicative basis, I would say in total 0.001 milliseconds saved, but 92x, not bad. The other thing that we did was move pretty much everything to the log phase. In OpenResty, if you remember, the log phase is after the response has been returned to the user. So often in OpenTelemetry SDKs, the guidance is to provide as many attributes as possible when you're creating a span. But because the log phase is happening after the thing has been returned, after the request has been returned to the user, it really doesn't matter how long it takes. So we just ended up, you start the span, you got to generate the random number, whatever, but attaching attributes, doing regexes, all that kind of stuff, we moved that all to the log phase to save some time. And we also managed trace volume using a technique called deferred sampling. I'm going to try to go over this real quick. I'd like to write a blog post or give a talk about deferred sampling, but it's in the editor's draft of the W3C trace context specification. And basically the idea is a request goes into the proxy, and the proxy generates a span. And if it doesn't have an inbound context, a trace context, then it generates a new trace ID and sends that on to the application. And then the application makes its own sampling decision and sends information about its sampling decision back to the proxy or some other app, right? Doesn't really matter. Sends that back to the proxy, and then the proxy examines the trace response header to decide whether to throw away the span or keep the span. This is important because in a lot of SDKs, the default sampling behavior is, hey, like if the previous link in the chain sampled in, then I'm going to sample in too. And if we had done that at Shopify, we would have overwhelmed our tracing infrastructure. We aspire to 0%, we aspire to not sample and keep everything, but we're not there yet. Okay, so here's some stuff that I skipped. LuaJIT doesn't love, OpenResty runs on LuaJIT, which is a just-in-time compiler for Lua. It doesn't really like big numbers, such as trace IDs, so that can get a little hairy. There was some fun that ensued when I had to convert config map entries in Ingress NGINX to Lua tables in the NGINX config. Oh, all right, I'm getting the hook. And very embarrassing to say to this audience, but I totally messed up the histograms, and I thought that the plugin was running extremely slowly. Then someone that I work with who knows math was like, Sam, your histograms are messed up, don't worry. So thanks, Reese. And thank you. Thanks to the venue staff. Thank you to the conference staff. Thanks to the attendees, the other speakers for sharing your knowledge. And whatever company bought me tacos yesterday, super appreciate it. And yeah, that's it. I'm friendly. Come and talk. And if you have questions, I think there's time.
There's definitely time for some questions. And we've got one right here on the edge.
No, just it's not. We're not using it because it's variety of reasons such as build issues, but it's definitely in the open telemetry. Yeah.
I misunderstood. I was wondering if you've done any benchmarking.
No.
Benchmarking on the C++.
Yeah, we haven't compared. I think this is adding 0.2 milliseconds to like 0.2, 0.4 milliseconds to P95 or P99, which, as we know, percentiles don't matter, but or I don't understand them properly, as evinced by the previous comment.
You're actually supposed to average them together.
Right. Okay. Yeah. So. Yeah.
Great.
Thanks.
Yeah, right here in the middle. Sorry, not middle, but upper middle. Yeah. When you messed up the global context, how did you find that in testing?
Oh boy, I don't even remember. Wait, the messed up the global context.
Well, you definitely would have had multiple requests.
Oh, yes, yeah. I didn't find it in. It was just in case you can't tell, like huge amount of anxiety flowing through me at all times. So I was freaked out about this from the get-go. So there's like a GitHub issue where I believe the first line is like, in Seinfeldian terms, what's the deal with OpenResty and sharing memory? So I spent about a week eventually arriving at the demo. The demo that I did is based on a ticket that I made in like August of 2022 where I'm like, oh my God, is this gonna work? But it did, so yeah.
All right, I think we're right in the middle now.
Do you have a sense of, like, with the additional information that you're packing your spans, like how many get dropped when traffic gets really high?
How many spans have been dropped?
Yeah, that's a really good question. Too many. I would say they're on a day-to-day basis, not a lot. Like I don't want to make stuff up, but like definitely single-digit percentages. But then during load tests and stuff, you can see that we're dropping more spans, and it is something we've got our best people working on the situation.
Top people.
Yeah, but come talk to me afterwards. I'll look at the graphs and get you some answers.
Awesome. And any other questions? All right. Yeah, just remember, if you do have any more, think of anything else, drop it in the speaker channels. Individual speaker channels are available for all of the speakers. So awesome. Another big round of applause.